we've taken a look at how to count electron domains for VSEPR or VSEPR theory. So we know how to count, and now we want to turn that into shapes. And this is actually going to take a couple of videos because there's a lot of shapes possible. For these, we're going to look at our most common molecular geometries, and those are situations where we find 2, 3, or 4 electron domains. Regardless of how many electron domains, though, VSEPR works on 2 main rules, and these rules are really related to each other. The first one is that electron domains want to spread out as far apart from one another, right? They're called electron domains because they involve electrons. Electrons have negative charges, so if negative charges get too close to each other, they repel. So when molecules form up, when chemical bonds form, and we get bonds around a central atom, they're going to spread out as much as possible so that they minimize all that bad repulsion. That's VSEPR. The other thing that happens, and you guys already saw this when we counted electron domains, is the idea that lone pairs and bounding groups are kind of similar to one another. They're all trying to repel, they're all trying to get far away from one another. And so we categorize lone pairs and we categorize bonds, but we also have these main categories that are just about electron domains, as you're going to see in a second. So for these 2, 3, and 4 electron domains in this video, the molecules that I'm going to draw, everybody's going to have a full octet or short octet, and by that I mean 6 electrons sometimes. And so we're going to see that in just a moment. But these electron geometries are the most common because they involve things that make a lot of compounds. So there's 2 things that we need to keep track of. The idea of electron pair geometry, and this is how the electron domains are arranged, and then molecular geometry. And so down here, what you see, these 5 names, trigonal, bipyramidal, seesaw, T-shaped, linear, those are molecular geometries. They're names for the shape of the atoms, right? The shape that the atoms make. But all 5 of these, right, have the same electron pair geometry. And that electron pair geometry is called trigonal bipyramidal. You notice that it overlaps with this name here. That's just the way that that's going to work, unfortunately. Some of the names do overlap. But you need to know how everything is arranged. And then you need to know specifically how the arrangement is divided up between bonds and lone pairs. So that's what we're going to take a look at in this next set of slides here. And the most important thing for you is to make a table that looks like this. Not kidding. Pause this video, get out a blank sheet of paper, and make this table. It's important to have this table on you, and it's important to memorize this table. You just want to be able, off the tip of your tongue, to call off this information. I don't ask you to memorize much, but this is a non-negotiable thing. Make this table and memorize it. Pause the video and I'll wait. All right, what I want you to understand is that this thing right here, this hybridization column, right? It's going to be empty when you finish this video and the next video on VSEPR. That's okay. A later video will help you fill this in. But everything in these columns, we're going to do in this video and in our next video on higher order electron domains. Again, pause the video, make this table, and memorize this table. I cannot tell you strongly enough that you need to memorize what I'm about to tell you. All right, first line in your table, you're going to put in 2 electron domains, and the name for that geometry is linear. Think about it. If I have 2 electron domains, the way that they can get the farthest apart from one another is to be in a straight line. And so this bond angle here from oxygen to carbon to oxygen, so we'd say OCO bond angle, is 180 degrees, a straight line. 2 bonds with no lone pairs. And carbon dioxide is one example, but there are others. So if you count 2 electron domains, and both of them are bonds, This is what we call a linear shape. That one makes a lot of sense. Let's start breaking it down for more complicated ones. Here's 3 electron domains. And what I want you to know is that the parent, right, for the electron geometry, so this is the electron pair or electron domain, the parent name for all of these shapes, if you count a total of 3, is trigonal planar. And if all 3 of those are bonds and none of them are lone pairs, that's what we call a trigonal planar molecule. And SO3, this is the neutral SO3 molecule, which looks like this: 3 double bonds around the sulfur and no lone pairs. Yeah, there are lone pairs on the oxygen, but they're not important to VSEPR. VSEPR doesn't care about the peripheral atoms. VSEPR only cares about the one in the middle, which is sulfur. All of those bond angles are 120 degrees. I'll show you a 3D picture of this in a little bit to help you make sense of it. Now, in 3 electron domains, it's possible that some of them could be bonds and some of them could be lone pairs. And that's what we have with the SO2 molecule, because we've drawn this on other slides. SO2, as a Lewis structure, has a lone pair on the sulfur, so different from carbon dioxide, which didn't have lone pairs. And again, yes, there are lone pairs on the oxygen. VSEPR doesn't care. VSEPR only cares about sulfur. So I see 2 bonds and a lone pair. And I'm going to take off my telestration just to make it easier to do what we're going to do. 2 bonds and 1 lone pair is called bent. And that OSO bond angle is around 120 degrees, right? So from here to here to here, that angle is 120 degrees. By the way, we can actually be a little bit more specific than that. We can say it is less than 120 degrees, because what happens is lone pairs reduce bond angles. Remember how I said in the rules of VSEPR that lone pairs and bonds take up similar amounts of space? That's why I said similar. Lone pairs take up a tiny bit more space. And so what happens is when that lone pair is there, instead of having this perfect 120 degree angle, the lone pair squishes the bonds just a little bit, right? So the sulfur is where my fists meet and the oxygens are at my elbows. And I get this bent shape. And that bent shape is from the lone pairs taking up space and making that bent. Let's see what this looks like in 3D, because it's kind of cool and it helps us visualize what's going on. What I've drawn here at the bottom are from your book's table. So the OpenStax book has 3D pictures and it shows the bond angles, but real molecules aren't ball and stick drawings like this. Real molecules are space filling. So in SO3, the sulfur is this big red ball and the oxygens are these 3 outside. And similarly, S and O and O. Real atoms are solid things, and bonds are just the space between the centers of the atoms. So the real molecule is in here, and the real molecule is in here with the bonds, right? And you can see that the way that these shapes come out, the SO3 molecule is flat, right? There's a flat plane, a flat piece of paper that this sits on. There's no oxygen sticking up or down or out. It's tilted, but it's still flat. And that 120 degree bond angle, changing color here, is right here. This is my 120. And you can see that it's like 3 pieces of pie dividing that 360 degree circle into 3 parts. That's how those 3 things got as far apart as they could. Sulfur, on the other hand, SO2, right, all this space up here, that's the lone pair. Lone pairs take up space. It's not like the lone pairs told the sulfurs and the oxygens that they could spread out again. The lone pair is here. And my 120 degree bond angle is also still here and still preserved. Let's look at one more common set of electron domains. So in this last one, we said the bonds and the lone pairs all add up to 3. Now let's see what happens when they add up to 4. This is what carbon loves to do for the most part in this 4 electron domain. And so we want to kind of watch out for that, because carbon is the backbone of a lot of stuff in the universe. So here's our 4 electron domains. And the parent name for 4 electron domains is tetrahedral. We'll see what a tetrahedron looks like in a little bit. And so, of course, if all 4 of those are bonds and none of them are lone pairs, we call that name tetrahedral. And that's a perfect 109.5-degree bond angle. How come it's not 90? Well, a tetrahedron, as we're going to see, is not a flat thing. There's going to be some bonds sticking out and up and to the sides. And so we have more than 360 degrees of space to play with. Let that kind of stick in. It's kind of fun to think about because we've got more than one plane. And so that 109.5-degree bond angle is the parent angle in tetrahedral. A good example of that is carbon tetrachloride. Yes, there are lone pairs on all of my chlorines here. Not important to this shape prediction that we're doing. And this is where Lewis structures fail, right? This Lewis structure looks flat. The real molecule is not flat. And so it hurts to draw 109.5 degrees here when it clearly looks like 90. That's because Lewis structures are for flat pieces of paper and real molecules aren't always flat. Our next shape is when I have 3 bonds and 1 lone pair, right? Still adds up to 4 electron domains. All 4 of those domains, the bond and the lone pair, are in a tetrahedron, but one of those domains is not an atom. So we call that name trigonal pyramidal. So remember in the previous one we had trigonal planar. It's a flat triangle. Trigonal pyramidal is those atoms are arranged in a pyramid shape. And you'll see in the picture, because again, this is our limitation of a flat paper. Yes, I can draw ammonia NH3 like this. This is a trigonal pyramidal molecule, but it's not looking like that in real life, right? This is how I can do it on a flat piece of paper. Our next option is 2 bonds and 2 lone pairs. So a good example of that is good old water. And this is an example of a bent molecule. Yeah, there's 2 bents, right? There's a bent where I have 1 lone pair and 2 bonds, and then there's a bent where I have 2 lone pairs and 2 bonds. And it should make sense again. Remember, lone pairs take up that extra space, that this angle gets more and more crunched. So there's a bent with around 120. There's a bent around 109.5. But again, less than 109.5 degrees because that lone pair does a little bit of crunching. That's the way we think about it in VSEPR. Let's see what these 3D shapes look like. So here's my 3D versions of 4 electron domains. Here's my tetrahedron. And you notice that there are funny things, right? There are wedges and dashed wedges, right? So here's a regular wedge. Here's a dashed wedge. What this means is that particular bond is coming out of the screen towards you. And the dashed wedge means away. This bond is pushing back out of the back of the screen. So there's one coming out at you, one coming towards you, and one coming away from you. And then there's 2, these straight ones, that are with the paper or with the board. And so that's why, again, you have more than 360 degrees of space to play with because you have more than one plane. They're not all flat to one another. You've got some sticking out and some not. And so that tetrahedron looks like this. And by the way, we think of the carbon in the middle here, and we think of a chlorine being here, and we think of a chlorine being here, and up top, and pushing away. And now you can see in that structure, there are 2 that are in the plane of the paper that I'm highlighting in red. This carbon chlorine bond is the one that they would draw as the wedge, that the solid wedge. And this one is the one that they draw as the dashed wedge because it's going away from you. A tetrahedral molecule is a 3-dimensional thing. It's not flat. Trigonal pyramidal, we've got our big old lone pair up here, and the nitrogen's in the middle. The hydrogens are on the outside. I've got 1 nitrogen in the plane of the paper. I've got 1 nitrogen-hydrogen bond that's sticking out of the board at me, and I can see that in this picture. And then I've got another one that's sticking away, and that big lone pair taking up space. With water, what happens is we just go ahead and get rid of the wedges. We have the lone pairs kind of sticking out away and towards. My hydrogen is here, or sorry, my oxygen is here. My hydrogens. Only the flat ones are left. So water's actually flat with the lone pairs taking up space. That's how we think about electron domains, and that's how they look in 3D. Again, cannot stress this enough to you. Make that table and memorize these things. Be able to say 3 bonds, 1 lone pair, trigonal pyramidal, or 2 bonds, 1 lone pair, bent. Be able to just spit those shapes out. Draw a Lewis structure, count the domains, spit out a shape. Practice that.